All right, so this is Mr. Smith here. We are finishing off section 6.2, rational exponents, so fractions in the exponent place. So one of the things we looked at yesterday was how to add these things. So we need to have the same root. Anytime we're adding, we need to have the same root, and we need to have the same number underneath. Okay, so in this case, I have the 4th root of 6, and I also have a 4th root of 6, so those I can add. And so here we have 6 4th roots of 6. Here we have 2 of them. And so when we add, we just get 8 4th roots of 6. It's important to see or to recall that this is multiplication in between here. Okay, that's going to come into play later on in the section. Okay, so that's multiplication there. So literally it's 8 times the 4th root of 6. But there we go. Now, if we want to do this problem, I notice both of those are cube roots. Both of those are cube roots, so I can add them as long as the number underneath the cube root is the same. And one, I have the cube root of 5. The other, I have the cube root of 625, which implies I can't add them as they are unless I can somehow rewrite this guy as the cube root of 5. Okay. And so we want to try to simplify the cube root of 625. And so we're going to look for perfect cubes. Again, I'd encourage you all to make a chart of perfect cubes down to maybe 8, perfect 4th powers down to 8, and perfect 5th powers, and just put it somewhere in your notes to reference back to. But hopefully you know that 5 cubed is 125. Okay, so 125 is a perfect cube, and so I can rewrite 625. I can rewrite 625 as the cube root of 125 times the cube root of 5. Okay, and of course, this first part just stays the same. Okay, so we get 4 times the cube root of 125 times the cube root of 5. And by the way, 125 times 5 is 625, so I haven't changed the problem at all. Okay, but we know that the cube root of 125 is just 5, right? 125 is a perfect cube. We picked it that way. So, again, the first part of this problem stays the same, but now I get 4 times cube root of 125 is just 5, and then here I have the cube root of 5. Okay. And so what ends up happening is we get 6 times the cube root of 5 plus 20 times the cube root of 5, and now I see I have 2 cube roots, both have 5 underneath them, so now I can add. Okay, so we have 6 cube root of 5 plus 20 cube root of 5, and so that's going to equal 26 cube root of 5. And that's the process. So, to go back, we had to simplify the cube root of 625. So we looked for a perfect cube. We found it. The perfect cube is 125. The cube root of that is 5. Again, this is all multiplication here, so this is just 20. And now we can add. I have 6 cube roots of 5. I have 20 cube roots of 5. When I add them together, I get 26 cube root of 5. Okay. Again, if you were to use a calculator will evaluate this, but it will only give you a decimal value for the answer. It wouldn't give you what we have here. Okay. All right. So now what we're going to do is throw in variables. So once we understand how to do this with numbers, let's make it more difficult on ourselves. We'll throw in variables. Okay. So here we go. I'm looking at the 5th root of 32x to the 15th. And so I'm going to break this into 2 pieces. I'll write as the 5th root of 32, which we should know by now. That should be one that's very comfortable. And the 5th root of x to the 15th. Okay, and that's multiplication between there. Okay. Now the 5th root of 32 is just 2. That piece should be fine. So maybe we'll just come over here and write the 2. But what is the 5th root of x to the 15th? Okay. And the way that you probably want to think about this is I would break up x to the 15th into 3 parts. Okay. So the 5th root And instead of considering it as x to the 15th, I would consider it as x to the 5th times x to the 5th times x to the 5th. Okay. And the first thing you need to do is to verify that x to the 5th times x to the 5th times x to the 5th is really x to the 15th. All right, but the rule says we just add the exponents, so 5 plus 5 plus 5 is 15. And now, hopefully, you can work through this. So what is the 5th root of x to the 5th? Well, those two should cancel each other out. If I take something to the 5th power, but then I 5th root it, it should just leave me with x. So the 5th root of x to the 5th should just be x here. The 5th root of this one should just be x. And the 5th root of this x to the 5th should be x. And so that leaves us with 2 times x cubed. Okay? So the 5th root of x to the 15th is just x cubed. Another way that some of you may want to see that is you may want to write this out as x to the 15th all to the 1, sorry, that's not what I wanted to write. It'll be x to the 15th all to the 1/5 power. All right, x to the 15th to the 1/5 power, which is x to the 15 over 3. Sorry, x to the 15th over 5, which is x cubed. Okay, so depending on which method you're more comfortable with, if you'd rather have the rational exponents, we could write this as x to the 15th to the 1/5 power. Remember, a 5th root is the same thing as the 1/5 power, and then 15 times 1/5 is just 3. Okay. Either way, we need to be comfortable at least doing that one way. Okay. All right, let's take a look at B. For B, all of this is to the 1/2 power, so we're going to bring the 1/2 power into every piece here. So we get 36 to 1/2 power, m to the 4th to the 1/2 power, so we just multiply, and then n to the 10th to the 1/2 power, so again we just multiply, and what we're left with, 36 to the 1/2 power, just 6. Remember, don't think 18, we're talking about a square root here, so it should just be 6. M to the 4 times 1/2 power would be m squared, and then n to the 5th. Okay, so that's not too bad. Okay. For part C, here I'm just going to rewrite this. Instead of considering it as the 3rd root, I'm going to consider it as everything to the 1/3 power. So a to the 9th, b to the 6th, and all to the 1/3 power. So the 1/3 gets applied to both exponents, and that's going to give us a to the 9 times 1/3, which is just 3, and b to the 6 to the 1/3 is just b squared. Okay. And on the last problem, I see a 42 divided by 6, so that's 7. I have x to the 4th divided by x to the 3/2. Okay, so the rule is subtraction, right? So 4 minus 3/2, 4 minus 1.5 is 2.5, right? So as a fraction, that would be x to the 5/2. Okay. I see a y to the negative 3rd in the denominator, so that means that'll come up to the numerator. So it would give us y cubed. And lastly, I have z to the 7th divided by z to the 5th. So we subtract there, and we're left with z squared. Okay, so again, all this is the application of the properties that we've seen throughout this section. Okay, are there questions there? Okay. So, for this problem, they want us to take the 4th root of a squared, b to the 6th. Okay. Again, for a problem like this, I find it a little bit easier to shift to the irrational exponent notation. You don't have to, but sometimes it makes it easier. So if you hit a wall going with the radical notation, I encourage you to shift to the rational exponent. And so now this 1/4 gets applied, and I get a to the 2/4 power over b to the 6/4 power. Now, of course, 2/4 just simplifies to 1/2. So this is just going to be the square root of a. This is going to be b to the 3/2. Okay, so everyone good so far? We're going to have to take this a little bit farther in a moment, but let's just make sure everything's good up until this point. So now I'm going to go back. I'm going to go back to our square root notation. So I get the square root of a over the square root, right? This is a 1/2 power, so it's a square root of b cubed. But here's the problem. Anytime we have a rational exponent where this number is greater than 1, right? 3/2 is greater than 1. What it means is that we could simplify it further. Anytime we have a rational exponent where this guy is greater than 1, we're going to be able to simplify this a little bit further. And the reason is because b cubed, right? I can think of b cubed, square root of a, but b cubed could be considered b squared times b. Right? Just breaking it apart. And the reason I chose b squared is because what's the square root of b squared? Just b. And so what this is going to give us is the square root of a over b square root of b. Okay, so anytime we get a rational exponent that's greater than 1, it's an indicator that we're going to have to go and simplify this more. Now let me show you a different way we could have thought of this. B to the 3/2 power, so let me write a to the 1/2 up here. And I could have just done this. B to the 3/2 is the same thing as b to the 2/2, or 2 divided by 2, times b to the 1/2. Right? Remember the rule is that we add the exponents. Right? We add the exponents. So basically, what I've done is this term takes care of the fact that here's the 1. Here's the 1, and now this is what's left over. And recall that 2/2 plus 1/2 gives us back to 3/2. So I haven't changed the problem. But what's b to the 2/2 power? Right, this is just going to be, this will just be b, kind of out of space here. Let me see if I can write this out here. So if we were to finish this off, we get a to the 1/2 b times b to the 1/2, which is exactly what this says, right? A to the 1/2 square root of a, b times b to the 1/2. Okay? So again, it doesn't matter which way you conceive of this. The first thing you need to see is if this exponent is greater than 1, we're going to have to simplify it further. That's the first thing we need to see. And the second thing is we can either write it back into the square root notation and now simplify, or we can just try to write it using our rational exponents. So I'll show a problem on this on the next slide, I think, but let me pause here for a moment. Okay, so this is probably the most complicated example that you would be expected to see or do, where we are simplifying a radical with variables inside. Okay, simplifying a radical with variables inside. And it doesn't matter which approach, you can leave this in the radical form, you can change this to the rational exponent form, do what is most comfortable for you. I think I'm going to try to approach this just leaving it in the form that it's in. Okay. And so what I want to do is I'm going to break up all of these pieces into separate cube roots. Okay, so I have the cube root of 8 times the cube root of x to the 7th times the cube root of y cubed times the cube root of z to the 11th. Now, two of these work out really nicely. The cube root of 8, just 2. The cube root of y cubed, just y. So let me rewrite this as 2y, and now I have the cube root of x to the 7th and the cube root of z to the 11th. Okay. Now, this is going to simplify more. This is going to simplify more. Okay. The way you could think of it is this would be x to the 7/3. This would be z to the 11/3. Okay. Both of those numbers are bigger than 1. Both of those are going to simplify farther. Okay. So what I'm going to do is I'm going to rewrite this into groups of x cubes. Okay, so the reason is because we're taking a cube root. So we have 2y, and then I have the cube root. And instead of writing x to the 7th, I'm going to write x cubed times x cubed times x. Okay, the reason is because x cubed times x cubed times x, it's just x to the 7th. Right? But I'm breaking it into groups of cubes because what's the cube root of x cubed? Just x. What's the cube root of this x cubed? X. So I'm going to get x squared out front. And then I'm going to be left with a cube root of just x. Okay, so I get here, in this case, 2y. And I'm going to have so again, the cube root of x cubed is just x. This is the first one. The cube root of this x is also just x, so we could just write that as x squared. And now we're left with the cube root of x here. Okay, this is the last piece. That's the remainder. Okay. All right. So now we need to do the cube root of z to the 11th. So why don't you, who are watching the video, and you in the class, why don't you try to simplify this piece by breaking z to the 11th into groups of z cubed. So we'll have z cubed times some more, right? And so you break it apart and try to figure out how this simplifies. And when we resume, I'll show you what it is. Pause the video now. Okay, so hopefully you saw that when you broke z to the 11th up into groups of z cubes, and again, if this was to the 4th power, we're going to break this up into groups of z to the 4th. Okay. And what we're left with here is a z squared, so we have the cube root of z squared left. And so now I'm just going to rewrite this. So we have 2y x squared. I have z cubed. And then I have the cube root of x times the cube root of z squared. And so really, since these are both cube roots, they can be combined under the same cube root. And so our final answer here is 2y x squared z cubed cube root of x z squared. That's how we do it. And that is the final answer there. Okay, so there's a lot there. Again, the idea is anytime we have, this would be z to the 11/3, so the exponent's greater than 1, or anytime this exponent underneath here is bigger than the root, that's an indication that we're going to be able to simplify, and we're going to need to. Okay, I think you'll have to do this on 1 or 2 problems in the homework, and that'll be it. And this is by far the most difficult problem you should expect. Okay. All right, so there's one other idea in this section, and that's combining or adding or subtracting expressions like this that have variables in them. Again, the same rules of addition and subtraction that we saw earlier still apply. So I have to be taking the same root, and I have to have the same variable underneath. Okay, so here's the 5th root, here's the 5th root, here I have y underneath, here I have y underneath, and so we can subtract. So I have 10 of these, I take away 6, and so we just have 4 left. 4 5th roots of y. Okay, right? I have 10 of these guys, I take away 6 of them, and I have 4 left. Okay, so that should feel pretty nice. And lastly, here I have a squared b to the 1/4. Here I have a squared b to the 1/4. Again, those all have to match. And then I have 3 of them plus 4 more. So we have 7 a squareds b to the 1/4. And there we are. And this roughly covers everything that you're expected to know about rational exponents. Okay. Lots of properties. Again, when there's just numbers, no variables, we can use the calculator. However, if you rely on the calculator for those parts, you're going to be in trouble when it comes to the variables because they use the same properties from the beginning of the section. Okay. So this concludes section 6.2. Thanks for your attention. Have a good day.